This is exercise 8.2, and we're going to do some problems from Q2. With Q2, there's two new rules introduced. If you remember back to the sentential logic, each operator had an introduction rule and elimination rule. It's going to be the same for the quantifiers. So the universal quantifier will have an introduction rule and elimination rule, and the existential quantifier will have an introduction rule and elimination rule. Those are inference rules, which means they can only be applied in one direction, and also that they can only be applied to whole sentences where the quantifier is the main operator. And we'll talk about that as we do some problems. But for 8.2, the rules that are introduced are universal elimination. And just like with the other elimination rules, that means basically you're getting rid of a sentence with the universal quantifier, and you end up with a sentence without the quantifier, so you eliminate it. And we're also going to look at existential introduction. And again, introduction implies we start with something without an existential quantifier and we introduce it in the conclusion. All right, these are just some examples, and let's do some problems so you can see how they actually work. So I'm doing some of the even problems since the odd are assigned for homework. And the first problem, number 2 here, has a universal quantifier for a premise, and then this sentence, which is just a sentence. Now remember the difference between x's, which are variables, those are placeholders, right? This sentence says for all x, x is a b, which is just another way of saying everything is a b. But notice this sentence doesn't say anything about any particular things, not specifically. It just says everything is a b. This sentence, though, C is the predicate, and G is an abbreviation for a particular subject. So this sentence says something like, Gerald is cold, or something like that, right? Cold, predicate, Gerald, subject. So we need to go from these two premises to this conclusion, CG and BG. All right, so we already have half of that. And again, remember, all the previous rules still apply from sentential logic. So we can get this conclusion with a conjunction introduction. And we already have half, we just need to get the other half, BG. So if you look at universal elimination, the way it works is this says for all x, fx, we can validly infer AF. And the reason for that is a relatively intuitive inference, right? If everything is an F, then pick a letter, pick a name, and that thing's going to be an F too, right? If I say everything in the universe is made of matter, then it follows that the sun is made of matter, and the moon is made of matter, and London is made of matter, etc., right? If everything is an F, then pick something, whatever individual you want, it's going to be an F. That's what the universal quantifier means. So our first sentence tells us everything is B, so we can validly infer then that G is a B, right? Because if everything is a B, then G is a B. And we justify that by universal elimination of 1. Now, just to save time, I'm going to use the capital A for the universal quantifier. You can use the capital A, or you can cut and paste the, maybe I should just cut and paste to save confusion. But because these quantifier symbols aren't on the keyboard, and you don't want the X, you just want quantifier elimination like that, and 1. So now we still need to get our conclusion, so we do CG and BG, and that's by our old rule of conjunction introduction of 2 and 3. So notice the old rules are going to work exactly the same as they used to, so that's why I kept saying throughout the semester this is all cumulative. It's not like you can just forget what we did before. It all still applies. Okay, so let's jump down to number 4. We've got two premises with universal quantifiers, and also just this disjunction with no quantifiers. And our conclusion is a disjunction. All right, so let's see. Again, we can use the universal elimination rule to get rid of these quantifiers. So if we do it for 1, we could get dA conditional EA. So notice how that works. You get rid of the quantifier and you replace the x's with some individual letter. Now, why do we pick A? And here, why do we pick G? Because that's what we need for our conclusion, right? Our conclusion is A, so we use A. But we could use any letter here, B, C, D, because this says for all x, if x is a D, then x is an E. So it follows that if A is a D, then A is an E. Right? So we picked the A because that's what we need to derive our conclusion. We could do the same thing with the second one. We get FA conditional GA, right? Get rid of the quantifier, replace the x's with a's. Now we can treat these just like ordinary conditionals, right? So we have DA conditional EA, FA conditional GA, and now we have a disjunction of their antecedents. Oh, sorry, I forgot to justify these rules. So this is copy and paste here. This is universal elimination of 1. This is universal elimination of 2. And now we can get our conclusion, EA or GA, by the rule called constructive dilemma. This was a, what did they call it? An added rule, right? That we don't, strictly speaking, need, but it makes our life easier. And remember, the way it works is it needs two conditionals. It needs three inputs, two conditionals and a disjunction of the antecedents. And as a result, it gives us the disjunction of the consequence. So that's CD3, 4, and 5. And that's our conclusion, so we're done. So again, don't forget all the old rules still apply. Alright, number 6. So here again we've got two universal predicates or premises, and then we've got two plain old sentences. You can see right away we could do a modus ponens, or we could do a conditional elimination and get not ES. And then we can do RS conditional DS by universal elimination of 1. Then we can do the same thing on premise 2, DS conditional ES by universal elimination of 2. So now our conclusion is there exists, it's an existential, right? There exists an X such that X is not an R, right? So there exists something that's not red, or whatever R stands for. Right, so we're going to need to do a existential introduction, and the way that works, and again this is a very intuitive inference, if I know that A is an A, if I know that Al is Albanian, then I can validly infer that there exists at least one X such that X is an Albanian, right? So if I know Al is an Albanian, I know there exists at least one Albanian, which is what the quantifier sentence is. Same, if I know Al is an Albanian and I know Al is bald, then I know there exists at least one bald Albanian. All right? So that's the inference, is if I know there's one, if I know of a particular thing that has a certain property, like being an Albanian, then I can infer validly that there exists at least one thing that has that property. So here, what we need to do is we need to get something that's not an R, right? So if I know, for example, that S is not an R, then I can validly infer that there exists something that's not an R. So basically what that means is I need to get not RS. Right? How do we do that? Well, we have a conditional, we have the negation of its consequence, so we can get not DS by our modus tollens rule, right? And that's 5, 7. You can do another modus tollens to get not RS. Right, so that's modus tollens, what is that? 6, 8. And that was what we needed. I mean, something that's not an R. Now we found the S is not an R, so we can do this we can get our conclusion then. And we justify that by writing existential introduction from 9. So 9 says something like Stan is not Romanian, and we know if Stan is not Romanian, there exists at least one thing X such that X is not Romanian. All right, so that's our conclusion. And again, think, just like with elimination and introduction rules before, if your conclusion is a existential quantified sentence, you're probably going to need to use EI to get it, and if you have premises that are universal quantifiers, you use universal elimination to get rid of them, right? Okay, so now we're down to number 8. Okay, so here we have universal quantifier, and we have AA. We need to get this existential quantifier sentence, all right? Now, 8 has a typo, and I posted this online, but I wanted to leave it in here just so I can explain it. So this says CC here in the conclusion, and you should never have an individual letter like that in a quantifier phrase. And similarly, you should never have a variable like this that's not in a quantifier phrase. All right, and there is one exception to that we'll talk about. So this is a typo. This should be this should be X instead of C. Right? You should never have a C like that or an individual letter like that inside of a quantifier phrase. So fix that. It should be CX. All right, now we can do a quantifier. We can do a universal quantifier elimination here. Now, again, you can only apply these inference rules when the universal quantifier is the main operator. When is it the main operator? When it's all the way to the left, when there's no negation in front of it. If there was a negation here, we could not apply universal elimination. And also when everything after it is in parentheses, right? So everything after this has to be together for this to be the main operator, right? So just to give you an example down here, if you had all X, AX, and all X, BX, right? You couldn't do a universal elimination here because the main operator here is the conjunction. It's not the universal quantifiers. Similarly, if you had negation AX, BX, you could not do a universal elimination here because the main operator here is the negation. So to be the main operator, and this goes for either quantifier, has to be all the way to the left with no negations to its left, and everything that comes after it has to be in parentheses together. Okay, so to do universal elimination here would give us AA, conditional BA, conditional not CA. And again, that's going to be the universal elimination rule of 1. So notice what we did. We got rid of the quantifier. We replaced all the X's with A's. Why A? Because that's what we need, to work with this. If we did B, then we couldn't do a modus ponens here, a conditional elimination. So we pick A because that's what we need. Since it's universal, we could pick anything we want, but we need A. So now we can do the conditional elimination so that's conditional elimination of 2 and 3. And let's see. Now we still need to get this. There exists an X such that X is not both a B and a C. So how do we do that? Well, we can do not BA or not CA by material conditional of 4. And now we do a De Morgan's of 5. And now we have something that looks like this as our conclusion. So we can do that. and that's by Existential Introduction.